Now that we know what the normal distribution is and how to use it, and we understand the concept of sampling distributions, we're ready to start estimating parameters and determining the sample sizes that we need in order to estimate those parameters. So we're going to start today by talking about estimating a population proportion. So there are three main concepts that we're going to talk about. The first is that of a point estimate. So a sample proportion is the best point estimate of our population parameter, or a population proportion in this case. We're going to talk about what a confidence interval is and how we can determine one and how we should interpret that. And then we'll also talk about how we can find the sample size that we need in order to estimate a population proportion. So first off, a point estimate. So a point estimate is a single value used to estimate a population parameter. The sample proportion p hat is the best point estimate of the population proportion p, like we said earlier. The reason for this is that p hat is called an unbiased estimator. So unbiased estimators, you might remember, is it's a statistic that targets the value of the population parameter. And when we say it targets, what that means is if we take all of the sample statistics, so we take our sampling distribution of that statistic, then we take the mean of that sampling distribution. That mean corresponds to the population parameter. So p hat was one that targets the population proportion p. So let's take a look at an example. So a Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said that they had a Facebook page. Based on that result, we're supposed to find the best estimate of the proportion of all adults who have a Facebook page. Well, the sample statistic, that sample proportion that I found, is the best point estimate of the population proportion. So we conclude that our best point estimate of the population proportion is 0.43. If we were giving that in percentage terms, if we were asked to estimate the percentage of all adults, we would use that 43% that we were given. With point estimates, it really is just that simple for proportions. Now let's talk about confidence intervals. So a confidence interval, or sometimes it's called an interval estimate, we'll probably be sticking to confidence interval here, is a range or an interval of values used to estimate a true value of a proportion parameter. A confidence interval, we sometimes abbreviate it with a capital C, capital I, for confidence interval. So in order to have a confidence interval, we have to have a confidence level. The confidence level is the probability, 1 minus alpha, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. The confidence level is also called a degree of confidence or the confidence coefficient. I skipped over this parentheses note of such as 0.95 or 95%. That's a really common one that we see. So really quick, just a quick touch of the relationship between the confidence level and alpha. Like we said, it was 1 minus alpha is how we get our confidence level. So if I want a 90% confidence level, I'll use alpha equals 0.1. For 95%, we use 0.05. And for 99%, we use 0.01. We'll see where those alpha values, why we even need those alpha values in just a little bit in an example. But for right now, let's talk about interpreting these confidence intervals. So when we say that we have a 95% confidence interval, that P is, say, between 0.05 and 0.55, there are both correct and incorrect interpretations of this that are very common to hear. So the correct interpretation, what we want to be getting into the practice of giving, is we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. A little bit more succinct way of saying that is still correct is to say we are 95% confident that the population proportion falls within the interval 0.405 to 0.455. A really common wrong way that you'll hear to interpret this is that there's a 95% chance that the true value of p will fall between 0.405 and 0.455. And another wrong one that's fairly common is that 95% of the sample proportions will fall between 0.405 and 0.455. A confidence level of 95% tells us that the process that we are using should result in the long run in confidence interval limits that contain the true population proportion 95% of the time. So if we go through this process that we haven't talked about yet, but we go through our process and we calculate what these 95% confidence intervals are. That's what's shown here as all of these red lines and the green line. These are all of our 95% confidence intervals that we found. You'll notice the true population proportion of 0.5 here falls within all but one of them. The one that it does not fall within is that green example. That's one out of the 20 different 95% confidence intervals that doesn't contain the actual true population proportion. And this is exactly what should happen with a 95% confidence interval. Most of the time, the population proportion should fall into that actual confidence interval that we've calculated through our process, and every once in a while, it won't. So now let's talk about finding critical values. We've talked about critical values for a very long time in this course. And critical value is the number on the borderline separating sample statistics that are significantly high or low from those that are not significant. And this is where alpha comes in. So these values have alpha divided by 2 as the area outside of them. So the number z sub alpha divided by 2 is a critical value that's a z-score with the property that at the border, that it is the border, that separates an area of alpha divided by 2 on the right tail of the standard normal distribution. Right. So let's take a look at an example. Let's find the critical value z sub alpha divided by 2 corresponding to a 95% confidence interval. So a 95% confidence interval corresponds to alpha equals 0.05. We do 1 minus 0.95 to get our 0.05. So alpha divided by 2 is going to be 0.025. So we want an area of 0.025 to the right of our z-value. So if I want that area to the right, then the area to the left needs to be 1 minus 0.025, which is the area of 0.975. And I need that value because remember our normal distribution table gives us z-values with the area to the left of those values. So we have an area of 0.975 that we're looking for in the body of the table, and we're looking for the z-score that corresponds to it. When we find this area of 0.9750 in the body of the table, the z-score that corresponds to it is 1.96. This is the picture that goes along with that. So you can see we're trying to find alpha divided by 2 area out in the tails of our normal distribution. And alpha divided by 2 is our 0.025. So the area to the left of the positive z-value that we're looking for is 0.975. And that z-value is 1.96. Similarly, you can look for the area to the left of the negative z-value being 0.025 and find that value to be negative 1.96. These being the positive and negative versions of each other is no surprise because the standard normal distribution is symmetric about the mean of 0. So Negative 1.96 and 1.96 will have the same areas out in the tails away from the mean. So in this previous example, we found our z-score of 1.96. Our other z-values that come up a lot for our 90% confidence interval, the one that has 5% or 0.05 area out in the tails each, is 1.645. And the 99% confidence interval, the one that has 0.005 area out in the tails, is 2.575. Now, there's this thing called the margin of error. So when data from a simple random sample are used to estimate a population proportion, the difference between the sample proportion and the population proportion is an error. So the maximum likely amount of that error is called the margin of error, and we denote it with a capital E. So there's a probability of 1 minus alpha, like our 95% or 0.95 for probability, that the difference between p hat and p is E or less. So the margin of error E is also known as the maximum error of the estimate, and it can be found by multiplying the critical value and the estimated standard deviation of sample proportions. So that critical value is z sub alpha divided by 2, and our standard deviation of sample proportions, we had this back a little ways ago, is the square root of p hat times q hat. Remember, q hat is 1 minus p hat, and divided by n, or sample size. And so this is the margin of error for proportions. So let's do it. Now that we have all of these pieces, we're going to be able to construct a confidence interval using an estimate of, or used to estimate a population proportion P. So all of the variables involved. We've got P, which is a population proportion. We've got P hat, which is a sample proportion. We've got N, or our number of sample values. We have E, our margin of error. And we have Z sub alpha divided by 2, which is our critical value. So before we can construct a confidence interval, we need to check a couple of things to see if we have some simple requirements met. The first is that the sample is a simple random sample. The second is that we are dealing with a binomial distribution. In order for the sample proportion to mean something, we need the conditions for the binomial distribution to be satisfied. Those were that we had a fixed number of trials. The trials were all independent of one another. There were 2 categories of outcomes, and the probabilities remained constant for each trial. Also added on, we need at least 5 successes and at least 5 failures. So when we construct our confidence interval, what we do is we take p hat and we subtract E, and we take p hat and we add E. And we are whatever percent confident that the actual population proportion falls between p hat minus E and p hat plus E. And E is just that margin of error that we talked about earlier. So our confidence interval, a lot of times we say that it's p hat plus or minus E, or we'll give it as an interval notation of p hat minus E, p hat plus E, with the open parentheses. Also, when you do this, we round confidence intervals for P to 3 significant digits. All right, so here's our procedure. Here's our process that we were talking about earlier but never went through, right? So here is the process for real. The first one, we're going to verify that the requirements in the preceding slides are met. All right. So that's our binomial distribution, 5 failures, 5 successes, that we've got random stuff going on for our sample. And then we can use technology or our normal distribution table. We'll use the normal distribution table to find our critical value. that corresponds to the desired confidence level. And then we'll evaluate the margin of error. And after we've done that, then we'll use the value of the calculated margin of error and the value of the sample proportion to find the confidence interval limits. And finally, we will round the resulting confidence interval limits to 3 significant digits. So let's take a look at an example of this. So this Gallup poll of 1,487 adults that showed that 43% of the respondents have Facebook pages. So our sample results are n equals 1,487 and p hat is 0.43. So we want to find the margin of error, E, that corresponds to a 95% confidence interval. We want to find the 95% confidence interval estimate of the population proportion P. And then we want to use our results to find, can we safely conclude that fewer than 50% of adults have Facebook pages? Assuming that we're a newspaper reporter, we're going to write a brief statement that accurately describes the results and includes all of the relevant information. So first things first, requirement check. Polling methods used by the Gallup organization results in samples that can be considered to be simple random samples. Check. We're good. All right. The next requirement, binomial distribution, binomial experiment. So the fixed number of trials is the 1,487 adults. The trials are independent because the response of one person doesn't affect the response of the other or of another. Then there's 2 possible outcomes. They either have a Facebook page or not. And the probability remains constant. The probability of having a Facebook page is fixed over time. So then we look at our 5. We're looking for 5 successes, 5 failures. So with 43% of the respondents having Facebook pages, the number with Facebook pages is 43% of 1,487, which is 639, definitely greater than 5. And if 639 of the 1,487 subjects have Facebook pages, the other 848 do not. Again, definitely greater than 5. So we have all of our requirements and we're ready to move on to constructing our confidence interval. Again, we could use technology, it would spit it out for us, but we're going to actually do some manual calculation and use our table instead. So the margin of error, we need to calculate that first. The margin of error is found using the formula that we saw earlier, the z sub alpha divided by 2 times the square root of p hat q hat divided by n. So z sub alpha divided by 2 for a 95% confidence interval, our critical value we found was 1.96. That was our z sub alpha divided by 2. Our p hat is our sample proportion, which was 0.43. Q hat is 1 minus p hat, which is 0.57. And finally, n is the number of trials, so the number of adults we have here is 1,487. So we'll put all of those values in and we will calculate away and we'll find an error of 0.0251636. So now we're ready to construct our confidence interval. So it's really easy. We take our p hat value, our 0.43, and our error that we just calculated, our margin of error of 0.0251636. And we're going to subtract and add that error from and to 0.43. So when we do that, we get a p-value that falls between 0.405 and 0.455. That's after we've rounded to our 3 significant digits. So now we're asked to answer this question of, do fewer than 50% of adults use it? Well, our confidence interval that obtained is always less than 0.5, and so it does appear that fewer than 50% of adults have a Facebook page between the interval of values between 0.405 and 0.455, and it's completely below 0.5, so we can be fairly confident that, in fact, 50% of adults do not have a Facebook page. All right. So our summary of results, what you might write as that newspaper reporter. So this is one statement that summarizes the results. There could be many other ways to put this. So 43% of adults have Facebook pages. That percentage is based on the Gallup poll of 1,487 randomly selected adults in the United States. In theory, in 95% of such polls, the percentage should differ by no more than 2.5 percentage points in either direction. That's our error coming out to play. From the percentage that would be found by interviewing all adults. So when we're analyzing results from polls, things that we need to consider. The sample should always be a simple random sample, not an inappropriate sample. If it's an inappropriate sample, then we can kind of disregard the results as not being valid. The confidence level should be provided. They should always tell you what the confidence level is, and if they don't, again, there's suspicion to be cast there. The sample size should also be provided. If that is not provided, or if you go through and you ran the checks based on the sample size that they gave you and the proportion they gave you, and it doesn't match those, especially the greater than 5 situation, then again, we've got issues and potentially doubt to be thrown. So you should always be looking for those 3 pieces of information. All right. Now, except on relatively rare cases, the quality of the poll results depends on the sampling method and the size of the sample. The size of the population is not usually a factor. So it's a mistake to think that because the sample size is a small percentage of the population size, then the results of the poll are not valid. So if we were trying to figure out something about all adults in the United States and we only polled 1,000 adults, that percentage of the population is very small, and it might be tempting to say the poll must not be valid, but that's not actually the case. As long as things work out otherwise, that poll can actually be very reliable. So now, what if you were given a confidence interval and you wanted to find the point estimate or the margin of error? A lot of times people will report the confidence interval and not give you the point estimate or margin of error. So you can find those things if you're given a confidence interval. It's really quite simple. To find the point estimate, we're trying to find the mean between the upper and the lower bound of our confidence interval. To do that, we take our upper confidence interval limit and our lower confidence interval limit, we add them together, and we divide by 2. To find our margin of error, we're trying to find half of the distance between our upper and our lower limit. To do that, we take our upper confidence interval limit, subtract from it our lower confidence interval limit, and then we divide by 2. So let's take a look at a write-up of this. Might say something like, our 95% confidence interval, 58% to 81% in this case. All right. So we say, okay, what was p hat and what is the margin of error? So 95% confidence interval is 0.58 to 0.81 from that statement of 58% to 81% that I read before. The point estimate p hat is that mean of those 2 values, so we add them together, 0.58 and 0.81, and then we'll divide by 2. And when we do that, we get 0.695, which is what they were rounding to 70% in their write-up. And then we can find the margin of error as well. So we take the 0.81, subtract from it the 0.58, so upper minus lower, and divide by 2. We're finding half of the distance in between. And when we do that, we get 0.115. So our error is 0.115. Finally, the last thing we want to talk about today is determining the sample size. So to find the sample size required to estimate a population proportion, that's what we want to do. So again, we have all of our same variables that we've been talking about before. We've added p in as our population proportion compared to p hat, our sample proportion. Now, to calculate what our sample size must be, when we know a point estimate p hat for a sample, we know a sample statistic, then we calculate n with taking z sub alpha divided by 2, squaring it, and taking p hat times q hat, and dividing by the error squared. Now, when we don't know p hat, then we don't have that sample estimate, what we do is we assume that p hat times q hat is the maximum value that it can be under the circumstances that p hat plus q hat has to equal 1. That maximum value is actually 0.25, taking p hat to be 0.5 and q hat to also be 0.5. So also really important, if we compute a sample size n and it's not a whole number, we need to round. We need n to be a whole number. And so the decision needs to be made between rounding up and rounding down. If we round down, then our sample size is just barely not sufficient. It's just barely not enough. But if we round up, it's always going to be sufficient. It's always going to be large enough. So always round up when you get a decimal for n, even if you have something like 1067.11 or 0.01, round up to 1068. So let's take a look at an example. So when the author was conducting research for this chapter, he found no information about the percentage of adults who made online purchases. Yet that information is extremely important to online stores as well as brick and mortar stores. If the author were to conduct his own survey, how many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? So we're first going to assume that a recent poll showed that 80% of adults make online purchases, and then we're going to also do this assuming that we know nothing. So let's go with 80% first. So with 80%, we have p hat equals 0.8 and q hat equals 0.2. Since we're dealing with a 95% confidence level, we have alpha is 0.05. So z sub alpha divided by 2 is z sub 0.025, which is 1.96. Now, also, our margin of error is 3%, or we want it to be less than or equal to 3, so 3%. So E is going to be 0.03. So we plug all of these things into our n equation, and when we do this, we get 682.951. We round up always to 683. So we must obtain a simple random sample that includes at least 683 adults to be 95% confident with a 3% error. Now, instead, let's look and say we don't know of what p hat is. We don't know. All right. So if we don't know what p hat is, then we use the 0.25 in place of p hat times q hat. So again, putting in 1.96 and 0.03 and calculating, we get 1067.11. And again, always round up, 1068. So if we don't know anything about what p hat is, we don't have that sample statistic to work from, we must obtain a simple random sample that includes at least 1068 adults. So to be 95% confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 1068 adults, assuming no prior knowledge. But by comparing this result to our sample that we found in part A, when we had 683 would be needed, we can see that a larger sample is required to achieve the same results when we don't know anything about that p hat value. Now, there are other methods for calculating confidence intervals. This one that we looked at is not the only one. So what we looked at is called the walled confidence interval. There's also something called the +4 confidence interval. And it's really quite simple. All we do is add 2 to the number of successes and add 2 to the number of failures. So our number of trials goes up by 4. And in doing so, we actually get a better estimate of our confidence interval. Now, that's not the only other one. That's the simplest of the others. Just really quick, there's something called the Wilson score, which again is more accurate, but looking at that formula, you get an idea of why we maybe don't use it. The Klopper-Pearson method is another one that gets criticized for being too conservative. It's considered an exact method, and again, the calculations are super messy, like more messy than the last one, so we're not going to deal there. And ultimately, if there's lots of methods for doing this, like which one's best? And the answer to that is it depends on what your goal is. So the walled confidence interval that we looked at is the best one for like a teaching tool and getting a feel for what confidence intervals are, because it's the simplest computationally and it's decently reliable. The +4 confidence interval is almost as easy as that one, and it performs better. So it's better in that sense. The others are also could be considered better, but without technology to do calculations for us, we wouldn't necessarily want to use those. So really sticking with either what we went through today or thinking about this +4 as an alternative.